we are reading the design of computer instruction set and the CPU. In the last class, we have seen that how the computer instruction set can be designed and the reduced instruction set machines, then the current state of the art, actually all the machines nowadays are reduced instruction set. So, how the instruction set are selected, how it can be designed, how it is what are the hardware implementation of it, that already we have read. Today we will start discussion on the design of CPU, and first we will see the design of ALU in this class. So, CPU contains 3 elements: the registers, the ALU, the arithmetic logic unit, and the control unit or CU. Now, already when we have discussed, we read the different type of register designs. There we have seen the how shift registers can be designed using flip flops, the barrel shifter, or what we can tell that this is actually a more than 1 bit transfer, that called the barrel shifter, the 4 by 4 or 8 by 8 barrel shifter, 16 by 16, how they can be designed, already we have read that part. Now, the arithmetic logic units, as its name implies, the arithmetic units. So, it has actually 2 parts. One is the ALU design, the arithmetic unit and the logic unit. Now, the ALU design means the combination of 2, the arithmetic unit and the logic unit, how they can be combined to form a ALU, whether it is a low scale, whether it is a upper scale ALU or larger ALU can be designed, that we will read in this class. Now, the arithmetic unit means the different types of adders, multipliers, subtractors, actually all type of arithmetic operation the unit does. And earlier classes we have read different types of adders, the ripple carry adder, normal, carry look ahead adder, carry save adder, the Wallace tree adder. Similarly, for multipliers we have seen the normal multiplier, the Booth's multiplier, the first multiplier, the array multiplier, different type of multipliers we have already read. So, actually arithmetic unit, how it can be designed, already we have read. Now, the logic units are nothing but our logic gates. It can be a simply one gate, AND, OR, NOT, NAND, or the combination of AND, OR, NOT gates, or in one word we can tell, we have read the Boolean equations, or how the logic outputs or the outputs can be generated from the combination of logic gates. So, already we have read this part also. So, basically the different units of ALU means the arithmetic unit, the logic unit, how they can be designed, already we have read. Today we will read that how the using these different units, the arithmetic and logic units, how the ALU can be designed. And then the other part of the CPU is the control unit, that also we will read later. So, we start the ALU design. An ALU can be divided into 2 segments. Just now we have seen the arithmetic unit and the logic unit. Now, arithmetic unit performs operations, arithmetic operations, addition, subtraction, multiplication, increment by 1, decrement by 1, etc. Now, the operations, obviously it operates on some operands, and these operands can be of type signed or unsigned. Say binary coded decimal numbers or BCD numbers we read early, floating point numbers. So, the different arithmetic units can be designed based on the type of operands. So, some floating point unit or some if operands are BCD numbers or so simple signed or unsigned binary numbers. And logical unit performs AND or NOT, all these logical operations. Now, first we see the design of arithmetic unit. We know all the units or the different type of adders, multipliers, subtractors, that all of we already we read. Now, I am considering a two function arithmetic unit which generate addition and subtraction. See here the key element is a 4-bit parallel adder, and as the module does the addition or subtraction, so for that we need one multiplexer. So, it selects either addition or subtraction. So, one multiplexer is needed for that. Now, say the S is the select line of the multiplier, S is the select line. So, my design is such that if S equal to 0, then the output function is f equal to x plus y, that means it is a addition, else f equal to x plus y bar y complement plus 1, that means this is the 2's complement subtraction, that means x minus y. So, if it is if s equal to 1, if s equal to, else means if s equal to 1, select is 1, then it is a minus. So, this is a simple logic. Say I have a adder, already we have seen how the adder can be designed. Say I have a subtractor, Now, this is a multiplexer, it has some select line, say adder goes to 0 line, subtractor goes to 1 line. So, if s equal to 0, it will, the adder is passed as a output. So, this is a f is a addition. If s equal to 1, say s equal to 1, then this value will be passed. And then F is a subtraction. So, this is a one simple design which does the either addition or subtraction together. So, we are calling this is a two function arithmetic unit. Now, if we see the design, say this is a this is a 4-bit parallel adder. This is a 4-bit parallel adder. So, say it has 4 bit. So, these are x0, these are my x, this is x0, x1, x2, x3, and these are my y lines. So, this is y0, y1, y2, y3. Now, notice here we have given 4 multiplexers here and the inputs are either y0 or y0 complement. Similarly, either y1, y1 complement, y2, y2 complement, y3, y3 complement. Now, these select lines, say this is the select lines. Say select lines, select S. Now, if S is 0, then y0, y1, y2, y3 uncomplemented values of y's are selected, and as if these are generating the output, the say 4 output bits, the T0, T1, T2 and T3. So, these are my function f. So, f is a addition. Now, if s equal to 1, then if select line is 1, then actually these all the complemented values of y, y0 bar, y1 bar, y2 bar and y3 bar will be selected, and then the function will be that x0, x1, x2, x3 and it will be added with y0 bar, y1 bar, y2 bar, y3 bar. So, actually this is a subtraction. So, what we can tell that this is my C in and here is a C out. So, using 4 multiplexers with one select line, that means 2 to 1 marks, 4 to 2 1 marks, that one 4-bit parallel adder as well as a one subtractor, 4-bit subtractor can be designed in this way. Now, we see a two function logic. Earlier we have seen a two function arithmetic unit. Now, we see a two function logic unit. See, in the example, last example, if s equal to 0, then it was a AND. If s equal to 1, then it was a subtract. Now, we are designing a logic that if s equal to 0, that means select line of the multiplexer is 0, then the function g is x and y, else the function is x XOR y, either it is doing AND or it is doing a XOR. Not and OR can also be derived by the following Boolean identities. Means using these XOR and AND, because the if it is 1 XOR x, we know the XOR function. Say if it is A XOR B, A XOR B, we know the truth table of this thing is actually function is A B bar plus A bar B So, 1 XOR x, 1 XOR x means 1 and x bar plus 1 bar dot x. Now, this is nothing but x bar plus 1 bar is 0. So, this portion will, this is ANDed with 0 means nothing will be there. So, this is a x bar. So, that is written here that 1 XOR x is nothing but a complemented value, that is a NOT. So, NOT can be designed using XOR. Similarly, x or y is nothing but x XOR y XOR xy. So, again using the XOR logic, another level of XOR. So, again what we can tell that if I have I know, or I can design a, say this is a XOR B, then we can do that x XOR y, and then it can be, say it is a C equal to x XOR y and D equal to x and y. Then G equal to C XOR D will give the C or x or y. It will give x or y. So, that x or y is x XOR y XOR xy. So, actually x XOR y that we have written as a C, and then C XOR and the xy is written as a D, then this is C XOR y is nothing but XOR y. So, actually if we can realize AND and XOR, then using these two logic, NOT and OR can also be designed. So, this 4-bit 2 function logic unit that we can give, that if it again this is a 4-bit. So, outputs are x 0, y 0, then it is the AND is fed to the 0 input of the multiplexer and the XOR goes to 1, x 1 y 1, x 2 y 2, x 3 y 3, the 4-bit value. Now, it has one similarly the marks as that select lines S. So, if S is 0, if S equal to 0, the 0 bit of the 0 input of the marks will be selected and it will be, so x 0 y 0, x 1 y 1, x 2 y 2, x 3 y 3. So, actually this is x and y, say g equal to x and y. So, we are getting z 0, z 1, z 2, z 3. Now, if it is, if s equal to 1, if s equal to 1, then the XOR will be selected, output of XOR will be selected. So, that means it will be x XOR y, then g will be x XOR y. So, again it is a 2 function logic units. In this way, using the multiplexers, we can always design a 2 function logic unit. So, we know that it is the multiplexer is a 2 to 1 multiplexer. The select line is 1, then it is a 2. Similarly, we can already we have read the how the bigger multiplexer can be designed, and if we have a 4 function, if we have a 4 function logic units or 4 function arithmetic units we need, then actually the way what we can do, we can take a multiplexers which have 4 input lines, 2 select lines, and the accordingly that particular output can be selected. These are my input lines, and here this what we can do, that here this can be a, this red box, this can be a logic unit or this can be a arithmetic unit. Now, as already we have read that instead of a larger marks, what we can do, we can design a larger marks multiplexers using smaller number of small marks multiplexers, or in more number of small multiplexers. So, in that way also we can do this, or we can design this logic unit and arithmetic units using the multiplexers. Now, we can combine the outputs generated by the arithmetic and logic units. As the ALU consists the ALU has two parts. One is arithmetic unit and the logic unit. And just now what we have done, the two-way or two function arithmetic units and add and subtract we have designed. Two function logic unit AND and XOR we have designed. If the output of the arithmetic unit that we can define as T0, T1, T2, T3, our AU outputs, and the logic units are G0, G1, G2, G3, then again another steps what we can do, we can combine the logic unit outputs and arithmetic unit outputs together by using some multiplexers. So, what we can do now, say the T0, say T0, T1, T2, T3, the output of the arithmetic units come to that first line, the 0th line. Similarly, the Z0, Z1, Z2, Z3 comes to the other multiplexer inputs. And as usual it has some select lines. It has the select lines S. Now, if S equal to 0, then say these are my Z0, Z1, Z2, Z3. So, if S equal to 0, the Z is actually the arithmetic units. If S equal to 1, the Z is output is the output of logic units. So, in this way we can combine the arithmetic and logic units again using another level of multiplexers. So, if we see the schematic representation, whatever be the unit, just as an example we have seen very small two function arithmetic units, addition and subtraction, and two function logic units, the add and the XOR. Now, it can be any complex arithmetic functions, it can be any complex logic unit functions. We want to combine these together. So, this is a schematic representation of 4 functions. So, this X is a 4-bit bus, Y is also 4-bit, and this is arithmetic unit, again the output is 4-bit bus, this is a F, it goes to the multiplexer's 0 line. Then the logic unit, again this is a 4-bit and it has 2 select lines because it has a 2 levels of multiplexers. So, this is S0 select lines S0 and S1. So, actually the S0 lines, it will select whether arithmetic units we need arithmetic functions or we need logic functions. And then S1, if S1 is selected, then which output will be we want, say arithmetic unit, or we want that logic unit as the output functions. Again this will be the 4-bit. So, this is the overall schematic representation. See here the select lines are, this is a 2-bit and the 2 levels of multiplexers are there. Here is actually S0 selects which type of arithmetic unit, because it all are 2 function arithmetic units or 2 function logic unit. So, S0 selects which function will select and S1 selects that which unit to be outputted, arithmetic or logic. So, this is the schematic representation. So, if we see the truth table controlling the operation of this ALU, so this is a truth table. So, I have 2 arithmetic or my arithmetic unit consists 2 functions. One is addition, another is subtraction, the 2's complemented subtraction. So, if see my S1 is 0 because this is a second level mark selection, S1 is the second level mark selection. So, this becomes 0. Now, if S0 is 0, addition is selected, if S0 is 1, the 2's complement subtraction is selected. Now, that means that these two are my arithmetic units. So, if S1 is 0, always arithmetic unit is selected as the output, that means Z is the output of arithmetic units, and if S0 is 0, then it will be addition, if S0 is 1, then it will be a 2's complement subtraction. Now, the second level marks, if it is a 1, then obviously logic units are selected. So, these are my logic units and these are a Boolean and a XOR. So, if it is 0, again if S0 is 0, this is a X and Y, if S0 is 1, then this is a X XOR Y. So, in this way we can the truth table, this is the truth table for controlling the ALU operations. So far what we have seen, now if we draw the the schematic diagram. Say a 1 bit ALU which perform AND, OR and ADD. That means I am taking the logic operations as AND and OR, logic operations as and OR, and always this is the one function only, this is my arithmetic, the addition, arithmetic addition. So, what it has two input, if it is the two input functions, the A and B, then one AND is there, this is my AND, this is my OR, and the output goes to this as the input of the marks. And this is 1 bit full adder. So, it has two inputs A B and another input is carry in, and the output goes to the input to the marks. So, it has some marks as the some select lines, and accordingly the output will be, or the particular input will be selected as the output of the multiplexer. So, these we can tell the schematic of a 1 bit ALU. Now, say the full bit for the full adder, this is the logic diagrams for carry out and sum. Already we have several times we have read, we have the design of adders, the design of full adder, and we know that this is the if A, B are the two inputs and another is the carry in, say C, then we know that A B plus B C plus C A, that is my A B plus B C plus C A is my carry out. So, this is the simple logic diagram. Similarly, the sum is nothing but A XOR B XOR C for the full adder. So, if this is my A and this is my B two inputs, this is my carry in C, then this is sum is A XOR B XOR C. So, these are the logic diagrams. So, design trick is solve part of the problem and extend. That means, first 1 bit full adder is designed, this 1 bit full adder is designed, it has two parts, the carry and sum, just now we have seen, we have designed, and then the other logics, the one AND gate and one AND gate and one OR gate, that we can do, and then the multiplexers, it is fed to the AND, OR, ADD, and it is fed to the multiplexers, and depending on the select lines, the particular function will be selected, whether it is arithmetic, whether it is a particular type of logic unit AND or OR. So, 1 bit ALU with the logic functions AND and OR and the arithmetic function as 1 bit full adder can be designed. This is my 1 bit full ALU. Now, if I want a 4 bit ALU, so we have to add 4 such 1 bit ALU, and this is the diagram for that. So, now it is A0 B0. So, this as if this is 1 bit ALU, the block diagram is this is 1 bit ALU. So, it has two inputs A0 B0, carry in another input, and the output is, say I am giving result 0, because I do not know whether it is a logic functions, whether it is a arithmetic functions. And then the carry in, because if it is addition, then this carry will go as the input carry of the second ALU. So, this is again another 1 bit ALU, and similarly the another carry in 2 will propagate. Another 1 bit ALU. In that way, in this case, if it is a 4 bit ALU, 4 such 1 bit ALU are concatenated or appended with the previous carry out as the carry in of the next ALU, and it will be designed like that. So, this is a general schematic for n bit ALU. Now, we see how subtraction can be done. Already we have seen the adder can be used as a subtractor. Say a minus b is that nothing but a plus of minus b, you know. So, 2's complement, take the inverse of every bit and add 1. This is, we know that this is the 2's complement meaning. So, bitwise inverse of b, that we have earlier example we have denoted as negation of b or b complemented, and then minus a plus b means minus a plus negation of b plus 1, because inverse of every bit and add 1, this means the 2's complement. So, a plus negation of b plus 1 is a plus, if we consider this is as a negation of b plus 1 means b complemented plus 1, and b complemented plus 1 is nothing but a minus b. So, this is a plus minus b means a minus b. So, in this way we can, that means from the taking the inverse of every bit or complement of every bit, we can do the subtraction. Already we have done that. In this way we can do the subtraction. So, what will be the ALU for that? See that again we have taken a multiplexes, and this is actually the select line. This is the select, or we can tell this is the select line. So, if it is 0, then normal b uncomplemented b will go, but if it is select line is 1, then actually b complement is the implement. That means, every bit of b, if it is a n bit of n bit b, then every bit of individual bit is complemented, and that will be given as the input of a multiplexers. So, actually it will go to the output. So, this is a, if it is a 4 bit, then the 4 bit inverse of every 4 bit will get here. And so, this is my arithmetic logic units. Say it is a subtraction. So, here the 4 bit a values will go here, and the 4 bit b complemented values, and if the arithmetic unit is selected by this select line or that carrying, then actually that the subtraction will be done at the output of this particular ALU, and here is the carry out. So, in this way individually the subtraction we can see. So, the subtraction, if the subtraction is the arithmetic unit, then using 1 bit full adder and we can do this thing. So, this is my the two inputs A and B. Then say A comes as it is to the full input of the full bit adder, but here B is inverted, B is not. This is nothing but 1 XOR 1 XOR B. So, this is 1 XOR B means B complement. Or not, as already we have seen that B bar or B complement we can write as 1 XOR B. So, B complement is added to the full bit adder, and if that is selected, then this particular this particular adder will be actually a subtractor. 2's complement subtractor. Now, say we have taken the 2 ALU and actually we are considering the overflow. So, if it is a 32 bit, A is a 32 bit, B is a 32 bit, and we are taking that 32 such ALUs, that 1 bit ALU we have kept here. So, A0 to A31. So, here some more ALUs are there, A0 to A31, similarly B0 to B31 are fed, and these are the select lines S0 to S31, and it produces that the combinational logics to produce select, compare, the carry in, etc. So, how the overflow can be detected? Because whenever it is the addition or even subtraction, the overflow can be there. See that if we have the decimal values, that 0, 1, 2, 3, 4, 5, 6, 7, these are my binary values, it is a 4-bit representation. Now, for these decimal values, this is a 2's complement representation. So, these are for negative numbers, this is 4-bit 2's complement representation. Now, say we want to add 7 plus 3, 7 plus 3 is 10. See, if we see the 7 plus 3 is 10, but here if we add 7 plus 3, it gives that minus 6. That means, when two positive numbers, sum of two positive numbers, the result is a negative number, then actually the overflow occurs. Similarly, here minus 4 and minus 5. So, this is minus 4 is 1 1 0 0, 2's complement representation, minus 5 is 1 0 1 1. Now, if we add these two, 0 plus 1 is 1, 0 plus 1 is 1, 1 0 is 1, 1 1 0, this is carry 1. Now, see minus 4 minus 5, if we add, we are getting a 7, we are getting a 7 and that is a positive number. So, if the result or the sum of two negative numbers is a positive numbers, then overflow occurs. Similarly, here it is a negative numbers minus 6. So, how we can detect the overflow? The result is too large or too small to represent properly, and example is just now we have seen. When adding operands with different signs, overflow cannot occur. Now, overflow occurs when the two positive numbers is a very important thing, that two positive numbers and the sum is negative, or the other case is two negative numbers and the sum is positive. So, just now we have seen the two examples of each of the cases. So, how we can detect the overflow? These are the two cases, that this is two positive numbers 7 and 3, two positive numbers and the sum is negative, two positive numbers and the sum is negative. Here two negative numbers and the sum is positive. So, both the cases the overflow occurs. Now, how we can detect? So, this is overflow detection. So, if x y is 0 0, then x x or y is 0, this is my XOR truth table. Now, this is actually that 1 bit ALU. So, I have taken a 4 bit. So, if it is a, I have taken A0 B0, A1 B1, A2 B2, A3 B3, and these are my carry in 1, carry in 2, carry in 3. So, now the carry in 3 and carry out 3, if we take the XORs of these two, carry in 3 and carry out 3 and we take the XOR, then this will detect the, it will detect the overflow. So, this is the overflow detection logic. Now, zero detection logic. So, zero detection logic is just a one big NOR gate. Any non-zero input to the NOR gate will cause its output to be 0, because NOR is complement of OR. OR is that if any one, at least if one bit is, one input is 1, then it will be output will be 1. So, NOR is that if one bit is 1, this is my, this is actually my NOR gate. So, if any one is 1, then it will be a 0. So, that logic we can use for a zero detection. So, again if you use a 1 bit ALU, just there are 4 bit ALU, A0 B0 A1 B1 is given, and the 4 outputs, the result 4 results are, this is simply a NOR gate. This is simply a NOR gate, So, at 0 at the output gives a 0 detection. So, if we do the summary of the LU design process, that there are two main concepts. One is define and conquer, that means formulate a solution in terms of simpler components. So, if it is a LU means either arithmetic units or logic units, that first will be designed using gates or simple gates. Then design each of the components or sub problems and generate and test. So, given a collection of building blocks, look for ways of putting them together that meets the requirement. So, these are the two fundamentals or the two basic concepts for the ALU design process. Now, the today's quiz question is that one simple ALU design, the design an ALU to perform the following functions. So, again here we have taken the two function arithmetic units and two function logic units. So, if the select lines are 0 0, it will be addition. If it is 0 1, it will be a subtraction. If it is 1 0, it will be a simple AND. If it is 1 1, it is a or B. So, design an ALU so that it perform these arithmetic logic units. This is the quiz questions of this. So, today we have seen the arithmetic logic unit design, and next day we will continue the control unit design. We are discussing the design of a CPU. In the last class, we have read the design of arithmetic logic unit, the ALU, and today we will read the design of control unit. Control unit, as its name implies, actually it is the unit of mastering the interfaces of all other units of a CPU. So, first we see that what is the function of control unit. So, control unit translates or decodes instructions and generate appropriate signals to accomplish the desired operations. So, we have read the design of instruction set. There